Hi everyone, and welcome back from snowy northern Michigan. I am working from home because I'm having a hard heck time trying to motivate myself to go outside in the cold. It's going to get colder next week, so yeah, that'll be great. Anyway, we have a very long article today, so feel free to strap in, lock in, whatever you want to call it, or feel free to split this into two parts for watching because I'm definitely going to have to pause it multiple times to work around my heating here. But this is what I want to call everything you ever wanted to know about prompt engineering. So if you want to make $1 million in AI right now, feel free to perfect the art of learning to ask the bots questions because that is generating six-figure jobs right at the moment. So if you're a good search person and you're working in information science and you want to start making some real coin right at the moment, get into prompt engineering. Anyway, we have all these lovely people to thank for this prompt report, and it is systematic and very detailed. We're going to go through about half of it before the appendices, but that's still about 40 pages. So, yeah, strap in, and hopefully we will be able to understand it. Here is our abstract. Generative artificial intelligence systems are increasingly being deployed across diverse industries and research domains. Domain developers and end users interact with these systems through the use of prompting and prompt engineering. Although prompt engineering is a widely adopted and extensively researched area, it suffers from conflicting terminology and a fragmented ontological understanding of what constitutes an effective prompt due to its relatively recent emergence. Yeah, I have the same, I have that issue. I feel like you have to be overly specific with the bots, but that's a judgment call. Anyway, we established a structured understanding of prompt engineering by assembling a taxonomy of prompting techniques and analyzing their applications. We present a detailed vocabulary, 33 vocabulary terms, a taxonomy of 58 LMM prompting techniques, and 40 techniques for other modalities. Additionally, we provide best practices and guidelines for prompt engineering, including advice for prompting engineering ChatGPT and other state-of-the-art large language models. We further present a meta-analysis of the entire literature in natural language prefix prompting. As a culmination of these efforts, this paper presents the most comprehensive survey on prompt engineering to date. And that was published literally like a couple weeks ago. So, and I don't know why I am scrolling down that way. Like I said, this is a very long one. So we have introduction, meta-analysis of prompting, beyond English prompting, and I may skip the multilingual section because I'm a dumb yank and only really speak English, and a little French, but not enough to do prompting. Extensions of prompting, issues, benchmarking, and then I'm going to try to get through conclusions. And then there's all these fun appendices, which I might skim through, but probably won't sit and read. Data sheets, keywords, systematic review, formally defining prompts. Oh yeah, all sorts of exciting stuff. On the plus side, there are lots of images, so hopefully this won't be too bad for all of us. Transformer-based large language models are widely deployed in consumer-facing internal and research settings. Typically, these models rely on the user providing an input, aka a prompt, to which the model produces an output. Such prompts may be textual, write a poem about trees, or take other forms, images, audios, videos, or any combination thereof. The ability to prompt models, particularly prompting with natural language, makes them easy to interact with and use flexibly across a wide range of use cases. Knowing how to effectively structure, evaluate, and perform other tasks with prompts is essential to using these models. As empirically, better prompts lead to improved results across a wide range of tasks. Makes sense. A large body of literature has grown around the use of prompting to improve results, and the number of prompting techniques is rapidly increasing. However, as prompting is an emerging field, the use of prompts continues to be poorly understood, with only a fraction of existing terminologies and techniques being well known among practitioners. We perform a large-scale review of prompting techniques to create a robust resource of terminology and techniques in the field. We expect this to be the first iteration of terminologies that will develop over time. We maintain an up-to-date list of terms and techniques at learnprompting.org, and I'm going to have to bookmark that because, like I said, my abilities to talk to the bots right now are not particularly good. No, well, that just has to do with my frustration with not having children. There's a reason. Scope of study. We create a broad directory of prompting techniques that can be quickly understood and easily implemented for rapid experimentation by developers and researchers. To this end, we limit our study to focus on prefix prompts rather than on close prompts because modern LMM transformer architectures widely employ prefix prompts and provide robust support for both developers and researchers. Additionally, we refined our focus to hard or discrete prompts rather than soft or continuous prompts, and leave out papers that make use of techniques using gradient-based updates such as fine-tuning. Hard prompts contain only tokens, i.e. vectors, that correspond to words in the model's vocabulary, whereas soft prompts may contain tokens that have no corresponding word in the vocabulary. So it requires more thinking to do soft prompts, and they're continuous. You have to go back and forth and do that reiteration thing we talked about in a different article about orchestration. And yes, if you are hearing the heater, it did come on. I'm trying to find a place to break for this on the section's overview. So finally, we study task agnostic techniques, and these decisions keep the work approachable to less technical readers and maintain a manageable scope. Thank you so much, because I'm one of those less technical readers. So core prompting techniques, we have the text-based ones, and they're often derived from fundamental text-based prompting techniques, such as multilingual ones and multimodal ones for processing video and audio. And this goes to agents, which make use of the techniques, and we have the safety needs, the evaluation, and the security. So we discussed 7 core categories that are well described by the papers within our scope. So, the section's overview. We conducted a machine-assisted systematic review grounded in the PRISMA process to identify 58 different text-based prompting techniques, from which we created taxonomy with the robust terminology of prompting terms. Our goal is to provide a roadmap for the community when considering which prompting techniques to use. While much literature on prompting focuses on English-only settings, we also discuss multilingual techniques. Given the rapid growth in multimodal prompting, where prompts may include media such as images, we also expand our scope to multimodal techniques. Many multilingual and multimodal prompting techniques are direct extensions of English-only text prompting techniques. As prompting techniques grow more complex, they have begun to incorporate external tools such as internet browsing and calculators. We use the term agents to describe these types of prompting techniques. It is important to understand how to evaluate the outputs of agents and prompting techniques to ensure accuracy and avoid hallucinations. Thus, we discuss ways of evaluating these outputs. We also discuss security and safety measures for designing prompts that reduce the risk of harm to companies and users. Finally, we apply prompting techniques in 2 case studies. In the first, we test a range of prompting techniques against the commonly used benchmark MMLU. In the second, we explore in detail an example of manual prompt engineering on a significant real-world use case, identifying signals of frantic hopelessness, a top indicator of suicidal crisis, in the text of individuals seeking support. We conclude with a discussion of the nature of prompting and its recent development. So, what is a prompt? A prompt is an input to a generative AI model that is used to guide its output. Prompts may consist of text, image, sound, or other media. Some examples of prompts include the text: write a 3-paragraph email for a marketing campaign for an accounting firm, a photograph of a piece of paper with the words "what is 10 times 179" on it, or a recording with an online meeting with the instructions "summarize this." Prompts usually have some text component, but this may change as non-text modalities become more common. Prompt templates. Prompts are often constructed via a prompt template. A prompt template is a function that combines one or more variables which will be replaced by some media, usually text, to create the prompt. The prompt can then be considered to be an instance of the template. Okay, those of you that do RDA, instances, should be somewhat familiar. Consider applying prompting to the attack of binary classification of tweets. Here is an initial prompt template that can be used to classify inputs. Classify the tweet positive or negative. Write a poem about trees. Write a poem about the following topic. So each tweet in the dataset would be inserted into a separate instance of the template, and the resulting prompt would be given to the large language model for inference. So terminology. Always gotta love terminology. So the components of a prompt. There are a variety of common components included in the prompt. We summarize the most commonly used components and discuss how they fit into prompts. And I think I spoiled the exciting... No. That was the previous 1.2 figure. Directive. Many prompts issue a directive in the form of an instruction or a question. This is the core intent of the prompt, sometimes simply called the intent. For example, here's an instance of a prompt with a single instruction: tell me 5 good books to read. Directives can also be implicit, as is one-shot case, where the directive is to perform English to Spanish translation. Night, knock, morning. Okay, so examples are also known as exemplars or shots, act as demonstrations that guide the generative AI to accomplish a task. The above prompt is a one-shot, i.e. one example prompt. Output formatting is often desirable for the generative AI to output information in certain formats, for example, CSV, Markdown, XML, or even custom formats. Structuring outputs may reduce performance on some tasks. However, Kurt point out that various flaws and show that structuring outputs may actually improve performance. Here's an example of how you might format a prompt and output information as a CSV. So, summarize this into a CSV. Style instructions are a type of output formatting used to modify the output stylistically rather than structurally. For example, write a clear and curt paragraph about llamas. A role, known as a persona, is a frequently discussed component that can improve writing in style text. For example, pretend you are a shepherd and write a limerick about llamas. It is, this sounds like my information instruction lessons where I look up pandas. Anyway, panda's easier to spell than llama. It is often necessary to include additional information in the prompt. For example, if the directive is to write an email, you might include information such as your name and position so the generative AI can properly sign it. Additional information is sometimes called context, although we discourage using this term as is overloaded with other meanings in the prompting space. So terminology of prompting in this lovely chart. Print this off if you need it. So terms of links to the appendix are not sufficiently critical to describe in the main paper, but they are important, and more prompting techniques in figure 2.2. So 1.1, the technique, the template, the engineering, the fine-tuning, which becomes prompt-based learning, prompt-based tuning. Prompt engineering becomes technique, meta-prompting, answer, conversational. The template, just I guess it's sort of hung out on here. We talk about it a little bit. And then there's prompting, context, context window priming, prompting technique, and context zero shots, all these exemplars, discretes, user systems, orthogonal prompting. This is all stuff that by the end of this, we will have some understanding of what is going on, I promise you, maybe. Verbalizer, extractor, and answer triggers. Yeah, that's fun. Okay. Moving right along. Terminology within the prompting literature is rapidly developing. As it stands, there are many poorly understood definitions and conflicting ones. The lack of a consistent vocabulary hampers the community's ability to clearly describe the various prompting techniques in use. We provide a robust vocabulary of terms used in the prompting community, and less frequent terms are left into Appendix 8.2. In order to accurately describe frequently used terms like prompt and prompt engineering, we integrate many definitions to derive representative definitions. So prompting is the process of providing a prompt to generative AI, which then generates a response. For example, the action of sending a chunk of text or uploading an image constitutes prompting. A prompt chain, activity prompt chaining, consists of two or more prompt templates used in succession. The output of the prompt, generally used by the first prompt template, is used to parameterize the second template, continuing until all templates are exhausted. So basically, you feed one thing in and it creates or generates an output for the next thing, and so on. Prompting technique. A prompting technique is a blueprint that describes how to structure a prompt, prompts, or dynamic sequencing of multiple prompts. A prompting technique may incorporate conditional or branching logic, parallelism, or other architectural considerations spanning multiple prompts. Prompt engineering is the iterative process of developing a prompt and modifying or changing the prompting technique that you are using. A prompt engineering technique is a strategy for iterating on a prompt to improve it. In literature, this will often be automated techniques. In consumer settings, users often perform prompt engineering manually without any assistive tooling. Yes, let me tell you about Google search engine attempts. Exemplars are examples of a task being completed that are shown to a model in a prompt. So dataset inference, so figure 1.4, prompt engineering process consists of 3 repeated steps: performing inference on a data set, evaluating performance, and then modifying the prompt template. Note the extractor is used to extract a final response from the large language model output. See more information on extractors. Okay, so we have data sets, the template, it generates something, and then it's extracting the utility function, and then we just keep doing this until we get something we want. Alright, short history of prompts. The idea of using natural language prefixes or prompts to elicit language model behaviors and responses originated before ChatGPT-3 and ChatGPT et al. And GPT-2 makes use of prompts as they appear to be first used in the context of generative AI by Fan et al. However, the concept of prompts was preceded by related concepts such as control codes and writing prompts in literature. The term prompt engineering appears to have come into existence more recently from Radford et al. And then slightly later from Reynolds and McDowell. However, various papers perform prompt engineering without naming the term, including Schick and Schultz, Gabo et al. For non-autoregressive language models. Some of the first works on prompting define a prompt slightly differently to how it is currently used. For example, consider the following prompt from Brown et al. Translate English to French, llama. Brown et al. Consider the word llama to be the prompt, where translate English to French is the task description. More recent papers, including this one, refer to the entire string passed to the LMM as the prompt. So meta-analysis of prompting. Systematic review process. In order to robustly collect a data set of sources for this paper, we ran a systematic literature review grounded in the Prisma process. We host this data set on Hugging Face and present a data set for the data set in Appendix 8.3. Our main data sources are Archive, Semantic Scholar, and ACO. We query these databases with a list of 44 keywords narrowly related to prompting and prompt engineering, as seen in Appendix 8.4. The pipeline. In this section, we introduce our data scraping pipeline, which includes both human and large language model assisted review. As an initial sample to establishing filtering criteria, we retrieve papers from an archive based on a simple set of keywords and Boolean rules. Woohoo, Boolean operators. Then human annotators label a sample of 1661 articles from the archive set for the following criteria. Include if the paper poses a novel prompting technique. Include if the paper strictly covers hard prefix prompts. Exclude if the paper focuses on training by back-propagating gradients. Not quite sure what that is. Include if the paper uses a masked frame and or window for non-text modalities. A set of 300 articles are reviewed independently by 2 annotators with 92% agreement. Next, we developed a prompt using GPT-4 1106 preview to classify the remaining articles. We validate the prompt against 100 ground truth annotations, achieving 89% precision and 75% recall for a combined F1 of 81%. The combined human and large language model annotations generate a final set of 1565 papers. Alright, so the Prisma systematic literature review process, we accumulate 4247 unique records from which we extract 1565 relevant ones. So they get this archive records after title deduplication, human review, thrown them out, after human review, check if the paper contains the word prompt, throw out another bunch. After removing papers that don't contain the word prompt, we have, 1,000 AI reviewed and then another whole bunch excluded, and after they use 1565 in this quantitative analysis. Alright, on to text-based techniques. We now present a comprehensive taxonomical ontology of 58 text-based prompting techniques, broken into 6 major categories, as shown in Figure 2.2. Although some of the techniques might fit into multiple categories, we place them into a single category of most relevance. Let's see this lovely figure before we go any further. So we have zero shot, fuse shot, thought generation, ensembling, self-criticism, and decomposition in this lovely rainbow chart. And as you can see, they all have subsets that we are going to get into, and it'll be great. In-context learning, or ICL, more acronyms, refers to the ability of generative AIs to learn skills and tasks by providing them with exemplars and or relevant instructions within the prompt without the need for weight updates and retraining. These skills can be learned from exemplars and or instructions. Note the word learn is misleading. In-context learning can simply be task specification. The skills are not necessarily new and can have already been included in the training data. See Appendix 8.9 for a discussion of the use of this term. Significant work is currently being done on optimizing and understanding. Whoa, okay. Few shot prompting is the paradigm seen in Figure 2.4, where the generative AI learns to complete a task with only a few examples. A few shot prompting is a special case of few shot learning, but does not require updating model parameters. We are going to have so many acronyms, and I am going to bungle them all. Okay, this is 2.2, so Figure 2.3, Figure 2.4. Okay, so somehow we missed over Figure 2.3. So exemplar quantity, include as many exemplars as possible. Exemplar ordering. Okay, so we highlight 6 main design decisions when crafting few shot prompts. Okay, so this does apply. Please note that recommendations here do not generalize to all tasks. In some cases, each of them could hurt performance. So include as many exemplars, reorder them, Trees are beautiful, I'm so excited, life is good, life is bad. So label distribution, provide a balanced label distribution. Okay, so, make them, don't give 3 angries and 1 happy, don't give 1 example. Label quality, ensure they are labeled correctly, that helps. As opposed to munging things up. I love life, makes me angry. Garbage in, garbage out, as my engineer father would say. Exemplar format, choose a common format. Don't make this like all sorts of interesting punctuation. Make it simple for the bot. And again, if we've been cataloging in RDA a while, we know that we have to make atomic data now to make the bot happy. Okay, simplicity, select similar exemplars to the test instance. Don't make YouTube ads suck, make me angry. Yeah, okay. So few shot prompting design decisions. Selecting exemplars for a prompt is a difficult task. Performance depends significantly on the various factors of the exemplars, and only a limited number of exemplars fit into the typical LMM context window. We highlight 6 separate design decisions, which I just fumbled through, including the selection and order of exemplars that critically influence the output quality. So, increasing the quantity of exemplars generally improves model performance, particularly in larger models. However, in some cases, the benefit may diminish beyond 20 exemplars. In the case of long context large language models, additional exemplars may continue to increase performance, so efficiency varies depending on tasks and models. So, there is an optimum number of examples to give them. Exemplar ordering. The order affects model behavior. On some tasks, it can cause accuracy to vary from below 50% to above 90%. Label distribution, as in traditional supervised machine learning, distribution of labels in the prompt affects behavior. For example, if 10 exemplars from one class and 2 from another class are included, this may cause the model to be biased towards the first class. Exemplar label quality. Despite general benefits of multiple exemplars, the necessity of strictly valid demonstrations is unclear. Some work suggests accuracy of labels is irrelevant. Well, that's not good. Providing models with exemplars with incorrect labels may not negatively diminish performance, so the bot is smarter than the human. However, under certain settings, there is a significant impact on performance. Larger models are often better at handling incorrect or unrelated labels. It is important to discuss this factor, since if you are automatically constructing prompts from large data sets that may contain inaccuracies, it may be necessary to study how label quality affects your results. So the exemplar format. The formatting of exemplars also affects performance. One of the most common formats is Q input A label, but the optimal format may vary across tasks. It may be worth trying multiple formats, see which performs best. There is some evidence to suggest that formats that occur commonly in the training data will lead to better performance. Exemplar simplicity, or similarity, excuse me. Selecting exemplars that are similar to the test sample is generally beneficial for performance. However, in some cases, selecting more diverse exemplars can improve performance. Intrusion selection. While instructions are required to guide large language models in zero-shot prompts, the benefits of adding instructions before exemplars in few-shot prompts is less clear. Ajith et al. Show that generic task-agnostic instructions, i.e. no instruction or complete the following task, improve classification and question answering accuracy over task-specific ones, such as what is the answer to this question. Concluding instruction following abilities can be achieved via exemplars alone. Interesting. While they may not improve correctness, instructions in few-shot prompts can still guide auxiliary output attributes like writing style. Huh. That's actually kind of interesting. And I'm sorry, I'm just looking at figures here just to make sure we aren't missing anything. So, and I already forgot. But ICL. So ICL from a training data prompt. In this version, the model is not learning a new skill, but rather using knowledge likely inside the training set. And the few-shot prompting technique, but looks like we'll get to that in a second here. Considering all of these factors, few-shot prompting, it can be very difficult to implement effectively. We now examine techniques for few-shot prompting in the supervised setting. Ensembling approaches can also benefit few-shot prompting, but we will discuss them separately. Assuming we have a training set, dtrain, which contains multiple inputs, dtrain x to I, and outputs, dtrain y to I, which can be used to few-shot prompt a generative AI rather than performing gradient-based updates. Assume that this prompt can be dynamically generated with respect to dtest xi at test time. Here is the prompt template we will use for this section following the input-output format. So exemplars dtest x to the I. K nearest neighbor, or KNN, is part of a family of algorithms that selects exemplars similar to dtest xi to boost performance. Although effective, employing K nearest neighbor during prompt generation may be time and resource intensive. Vote K is another method to select similar exemplars to the test sample. In one stage, a model proposes useful unlabeled candidate exemplars for an annotator to label. In the second stage, the label pool is used for few-shot prompting. Vote K also ensures that newly added exemplars are sufficiently different than existing ones to increase diversity and representativeness. Self-generated in-context learning. Okay, that's what ICL is. I will try to remember. Maybe I should write that down. Leverages a generative AI to automatically generate exemplars. While better than zero-shot scenarios when training data is unavailable, the generated samples are not as effective as actual data. That is unsurprising. Prompt mining is the process of discovering optimal middle words in prompts through large corpus analysis. These middle words are effectively prompt templates. For example, instead of using the common QA format, format. For few-shot prompts, there may exist something similar that occurs more frequently in the corpus. Formats which occur more often in the corpus will likely lead to improved prompt performance. And then there's more complicated stuff, such as lens, UDR, active example selection, leverage, iterative filtering, embedding and retrieval, and reinforcement learning, respectively. On to zero-shot prompting techniques, okay? In contrast to few-shot prompting, zero-shot prompting uses zero exemplars. You just ask it a question. Okay, there are a number of well-known standalone zero-shot techniques, as well as zero-shot techniques combined with another concept such as chain of thought, which we will discuss later. So role prompting, we will get to in a sec. Role prompting, also known as persona prompting, assigns a specific role to the Gen AI in the prompt. For example, the user might prompt it to act like Madonna or a travel writer. This can create more desirable outputs for open-ended tasks, and in some cases may improve accuracy on benchmarks. Style prompting involves specifying the desired style, tone, or genre in the prompt to shape the output of a generative AI. A similar effect can be achieved using role prompting. Emotion prompting incorporates phrases of psychological relevance to humans, such as "this is important to my career," into the prompt, which may lead to improved LLM performance on benchmarks and open-ended text generation. System to attention. First, asks an LLM to rewrite the prompt and remove any information unrelated to the question therein. Then it passes this new prompt into an LLM to retrieve a final response. Sim2M deals with complicated questions which involve multiple people or objects. Given the question, it attempts to establish the set of facts one person knows, then answer the question based on only those facts. This is a two-prompt process and can help eliminate the effect of irrelevant information in the prompt. Rephrase and respond instructs the LLM to rephrase and expand the question before generating the final answer. For example, it might add the following phrase to the question, rephrase and expand the question, and respond. This could all be done in a single pass, or the new question could be passed to the LLM separately. Our AR has demonstrated improvements on multiple benchmarks. Rereading. Rereading adds the phrase, read the question again, to the prompt in addition to repeating the question. Although this is such a simple technique, it has shown improvement in reasoning benchmarks, especially with complex questions. Self-ask prompts LLMs to first decide if they need to ask follow-up questions for a given prompt. If so, the LLM generates these questions, then answers them, and finally answers the original question. So this example of a one-shot chain of thought prompt. Jack has 2 baskets, each containing 3 balls. How many balls does Jack have in total? 1 basket contains 3 balls, so 2 baskets contains 3 times 2, 6 balls. Self-ask prompts large language models first decide if they need to ask follow-up questions for a given prompt, and if so, they generate the questions, answer them, and finally answer the original question. Thought generation encompasses a range of techniques that prompt the LLM to articulate its reasoning while solving a problem. This I like. Chain of thought prompting leverages few-shot prompting to encourage the LLM to express its thought process before delivering its final answer. This technique is occasionally referred to as chain of thoughts. It has been demonstrated to significantly enhance the LLM's performance in mathematics and the reasoning tasks. In Way et al., the prompt includes an exemplar featuring a question, a reasoning path, and the correct answer. It's shown in figure 2.8, and I think this was figure 2.7 up here. Nope, this was figure 2.8. Okay. Zero-shot chain of thought. The most straightforward version of chain of thought contains 0 exemplars. It involves appending a thought including phrase like, let's think step by step, to the prompt. Other suggested thought-generating phrases include, first, let's think about this logically. It uses LLMs to generate, let's work this out in a step-by-step way to be sure we have the right answer. Yang et al. Searches for an optimal thought inducer. Zero-shot chain of thought approaches are attractive as they don't require exemplars and are generally task agnostic. We note such techniques are often described using words like think that anthropomorphize models. We attempt not to use this language, but do use the author's original language where appropriate. Step-back prompting is a modification of chain of thought, where the large language models first ask a generic high-level question about relevant concepts or facts before delving into reasoning. This approach has improved performance significantly on multiple reasoning benchmarks for both Palm 2L and GPT-4. Analogical prompting is similar to SGICL and automatically generates exemplars that include chain of thoughts. It has demonstrated improvements in mathematical reasoning and code generation tasks. Thread of thought prompting consists of an improved thought inducer for a chain of thought reasoning. Instead of let's think step by step, it uses walk me through this concept in manageable parts step by step, summarizing and analyzing as we go. This thought inducer works well in question answering and retrieval settings, especially with dealing with large complex contexts. Okay. Tabular chain of thought consists of a zero-shot chain of thought prompt that makes the LMM output reasoning as a markdown table. This tabular design enables the large language model to improve the structure and thus the reasoning of its output. And then we have few-shot chain of thoughts. So this set of techniques presents the large language model with multiple exemplars, which include chains of thought that significantly can enhance performance. This technique is occasionally referred to as manual chain of thought or golden chain of thought. Contrastive chain of thought prompting adds both exemplars with incorrect and correct examples to the chain of thought prompt in order to show the large language model how not to reason. This method has shown significant improvement in areas like arithmetic reasoning and factual QA. Uncertainty routed chain of thought prompting samples multiple chain of thought reasoning paths and selects the majority if it is above a certain threshold calculated based on validation data. If not, it samples greedily and selects that response. This method demonstrates improvement on the MMLU benchmark for both GPT-4 and Gemini Ultra models. Complexity-based prompting involves two major modifications of chain of thought. First, it selects complex examples for annotation and inclusion in the prompt based on factors like question length or reasoning steps required. Second, during inference, it samples multiple reasoning chains, answers, and uses a majority vote among the chains exceeding a certain length threshold under the premise that longer reasoning indicates higher answer quality, in theory. This technique has shown improvements on 3 mathematical reasoning datasets. Active prompting starts with some training questions exemplars, then asks the LLM to solve them, then calculates uncertainty, disagreement in this case, and asks human annotators to rewrite the exemplars with the highest uncertainty. Memory of thought prompting. Leverage unlabeled training exemplars to build few-shot chain of thought prompts at test time. Before test time, it performs inference on the unlabeled training exemplars with chain of thought. At test time, it retrieves similar instances to the test sample. This technique has shown substantial improvements in benchmarks like arithmetic, common sense, and factual reasoning. Automatic chain of thought prompting. Zhang et al. Uses Wei et al.'s zero-shot prompt to automatically generate chains of thought. These can then be used to build a few-shot chain of thought prompt for a test sample. Decomposition. Significant research has focused on decomposing complex problems into simpler sub-questions. This is an effective problem-solving strategy for humans as well as generative AI. Some decomposition techniques are similar to thought-inducing techniques such as chain of thought, which often naturally break down problems into simpler components. However, explicitly breaking down problems can further improve LLM's model problem-solving ability. Yeah, see, I can't even say that well as an abbreviation. Least to most prompting starts by prompting a large language model to break a given problem into subproblems without solving them, then it solves them sequentially, appending model responses to the prompt each time until it arrives at a final result. This method has shown significant improvements in tasks involving symbolic manipulation, compositional generalization, and mathematical reasoning. Decompose prompting, decomp. Few-shot prompts cite an LLM to show it how to use certain functions. These might include things like string splitting or internet searching. These are often implemented as separate calls. Given this, the LLM breaks down its original problem into subproblems, which it sends to different functions. It has shown improved performance over least to most prompting on some tasks. Plan and solve prompting consists of an improved zero-shot chain of thought prompt. Let's first understand the problem and devise a plan to solve it. Then let's carry out the plan and solve the problem step by step. This method generates more robust reasoning processes than standard zero-shot chain of thought on multiple reasoning datasets. Tree of Thought, also known as Tree of Thoughts, creates a tree-like search problem by starting with an initial problem and then generating multiple possible steps in the form of thoughts as from a chain of thought. It evaluates the progress of each step makes toward solving the problem through prompting and decides which steps to continue with, then keeps creating more thoughts. Tree of Thought is particularly effective for tasks that require search and planning, which is why this one I've actually heard about in library science contexts. The rest not so much, but hey, we're babies. Recursion of thought is similar to regular chain of thought. However, every time it encounters a complicated problem in the middle of its reasoning chain, it sends this problem into another prompt call. After this is completed, the answer is inserted into the original prompt. In this way, it can recursively solve complex problems, including ones which might otherwise run over the maximum context length. This method has shown improvements on arithmetic and algorithmic tasks, though implemented using fine-tuning to output a special token that sends subproblem into another prompt. It can also be done only through prompting. Program of thoughts uses LLMs like codecs to generate programming code as reasoning steps. A code interpreter executes these steps to obtain the final answer. It excels in mathematical and programming-related tasks, but is less effective for semantic reasoning tasks. Faithful chain of thought generates a chain of thought that has both natural language and symbolic language, such as Python reasoning, just like program of thoughts. However, it also makes use of different types of symbolic languages in a task-dependent fashion. Skeleton of thought focuses on accelerating answer speed through parallelization. Given a problem, it prompts the LLM to create a skeleton of the answer and it sends subproblems to be solved. Then in parallel, it sends these questions to an LLM and concatenates all the outputs to get a final response. Metacognitive prompting attempts to make the LLM mirror human metacognitive processes with a 5-part prompt chain with steps including clarifying question, preliminary judgment, evaluation of response, decision confirmation, and confidence assessment. Yeah, that sounds the most like humans. Ensembling! In generative AI, ensembling is the process of using multiple prompts to solve the same problem, then aggregating these responses into a final output. In many cases, a majority vote selecting the most frequent response is used to generate the final output. Ensembling techniques reduce the variance of large language model outputs, often improving accuracy, but come with the cost of increasing the number of model calls needed to reach a final answer. Demonstration ensembling creates multiple few-shot prompts, each containing a distinct subset of exemplars from the training set. Next, it aggregates over their outputs to generate a final response. Mixture of reasoning experts creates a diverse reasoning experts by using different specialized prompts for different reasoning types, such as retrieval augmented prompts for factual reasoning, chain of thought reasoning for multi-hop and math reasoning, and generated knowledge prompting for common sense reasoning. The best answer from all experts is selected based on an agreement score. Max Mutual Information Method creates multiple prompt templates with varied styles and exemplars, and then selects the optimal template as the one that maximizes mutual information between the prompt and the large language model outputs. Self-consistency, weighing it all, is based on the intuition that multiple different reasoning paths can lead to the same answer. This method first prompts the large language model multiple times to perform chain of thought, crucially with a non-zero temperature, to elicit diverse reasoning paths. Next, it uses a majority vote over all generated responses to select a final response. Self-consistency has shown improvements on arithmetic, common sense, and symbolic reasoning tasks. Universal self-consistency is similar to self-consistency, except that rather than selecting the majority response by programmatically counting how often it occurs, it inserts all outputs into a prompt template that selects the majority answer. This is helpful for free-form text generation in cases where the same answer may be output slightly differently by different prompts. Meta-reasoning over multiple chain of thoughts is similar to universal self-consistency. It first generates multiple reasoning chains, but not necessarily final answers for a given problem. Next, it inserts all of the chains into a single prompt template and then generates a final response. Diverse creates multiple prompts for a given problem and then performs self-consistency for each, generating multiple reasoning paths. They score reasoning paths based on each step in them and then select a final response. Consistency-based self-adaptive prompting constructs few-shot chain of thought prompts by running zero-shot chain of thought with self-consistency on a subset of examples, and then selecting a high agreement subset of the outputs to be included in the final prompt as exemplars. It again performs self-consistency with this final prompt. Universal self-adaptive prompting builds on the success of consistency-based self-adaptive prompting, aiming to make it generalizable to all tasks. Universal self-adaptive prompting makes use of unlabeled data to generate exemplars and a more complicated scoring function to select them. Additionally, universal self-adaptive prompting does not use a self-consistency. Prompt paraphrasing transforms an original prompt by changing some of the wording while maintaining the overall meaning is effectively a data augmentation technique that can be used to generate prompts for an ensemble. Self-criticism. When creating Gen AI systems, it can be useful to have LLMs criticize their own outputs. This could simply be a judgment, is it correct, or the LLM could be prompted to provide feedback, which is then used to improve the answer. Many approaches to generating and integrating self-criticism have been developed. Self-calibration first prompts the LLM to answer a question, then it builds a new prompt that includes the question, the LLM's answer, and additional instructing answering whether the answer is correct. This can be useful for gauging confidence levels when applying LLMs and deciding when to accept or revise the original answer. Self-refine is an iterative framework where given an initial answer from the large language model, it prompts the same large language model to provide feedback on the answer and then prompts the LLM to improve the answer based on the feedback. This iterative process continues until a stopping condition is met, e.g. the max number of steps is reached. Self-refine has demonstrated improvement across a range of reasoning, coding, and generation tasks. Reversing chain of thought first prompts the LLM to reconstruct the problem based on the generated answer. Then it generates fine-grained comparisons between the original problem and the reconstructed problem as a way to check for any inconsistencies. These inconsistencies are then converted to feedback for the LLM to revise the generated answer. Self-verification generates multiple candidate solutions with chain of thought and then scores each solution by masking certain parts of the original question and asking the LLM to predict them based on the rest of the question and the generated solution. This method has shown improvement on 8 reasoning data sets. Chain of verification first uses the large language model to generate an answer to a given question. Then it creates a list of related questions that would help verify the correctness of the answer. Each question is answered by the large language model, and then all the information is given to the LLM to produce the final revised answer. This method has shown improvements in various question answering and text generation tasks. Cumulative reasoning first generates several potential steps in answering the question, then has the LLM evaluate them, decide to either accept or reject the steps. Finally, it checks whether it has arrived at the final answer, and if so, it terminates the process, but otherwise it repeats it. This method has demonstrated improvements in logical inference tasks and mathematical problems. Prompting technique usage. So as we have just seen, there exist many text-based prompting techniques. However, only a small subset of them are commonly used in research and in industry. We measure technique usage by proxy of measuring the number of citations by other papers in our dataset. We do so with the presumption that papers about prompting are more likely to actually use or evaluate the cited technique. We graph the top 25 papers cited in this way from our dataset and find that most of them propose new prompting techniques. The prevalence of citations for few-shot and chain-of-thought prompting is unsurprising and helps to establish a baseline for understanding the prevalence of other techniques. Benchmarks! In prompting research, when the researchers propose a new technique, they usually benchmark it across multiple models and datasets. This is important to prove the utility of the technique and examine how it transfers across models. In order to make it easier for researchers proposing new techniques to know how to benchmark them, we quantitatively examine which models and what benchmark datasets are being used. Again, we measure usage by how many times papers in the dataset cite the benchmark datasets and models. To find which datasets and models are being used, we prompted GPT-4 1106 preview to extract any mentioned dataset or model from the body of papers in our dataset. After we manually filtered our results that were not models or datasets, the citation counts were acquired by searching items from the finalized list on Semantic Scholar. Prompt engineering. In addition to surveying prompting techniques, we also review prompt engineering techniques, which are used to automatically optimize prompts. We discussed some techniques that use gradient updates, since the set of prompt engineering techniques is much smaller than that of prompting techniques. Meta-prompting is the process of prompting an LLM to generate or improve a prompt or prompt template. This is often done without any scoring mechanism using just a simple template. However, other works will present more complex uses of meta-prompting with multiple iterations and scoring mechanisms. Improve the following prompt. Autoprompt uses a frozen large language model as well as a prompt template that includes some trigger tokens whose values are updated via backpropagation at training time. This is a version of soft prompting. Automatic Prompt Engineer uses a set of exemplars to generate a zero-shot instruction prompt. It generates multiple possible prompts, scores them, then creates variations of the best ones, such as by using prompt paraphrasing. It iterates on this process until some desiderata are reached. Gradient-free instructional prompt search is similar to APE, but uses a more complex set of operations, including deletion, addition, swapping, paraphrasing, in order to create variations of the starting prompt. Prompt optimization with textual gradients is a unique approach to prompt engineering that improves a prompt template through a multi-step process. First, it passes a batch of inputs through the template and then passes the output, ground truth, and prompt into another prompt that criticizes the original prompt. It generates new prompts from these criticisms and then uses a bandit algorithm to select one. Protege demonstrates improvements over methods like APE and GRIP. RL prompt uses a frozen large language model with an unfrozen model added. It uses this large language model to generate prompt templates, scores the templates on a dataset, then updates the unfrozen module using soft Q learning. Interestingly, the method often selects grammatically nonsensical text as the optimal prompt template. Dialogue comprised policy gradient-based discrete prompt optimization is perhaps the most complicated prompt engineering technique, involving reinforcement learning, a custom prompt scoring function, and conversations with a large language model to construct the prompt. Answer engineering. Answer engineering is the iterative process of developing or selecting among algorithms that extract precise answers from large language model outputs. To understand the need for answer engineering, consider a binary classification task where the labels are hate speech and not hate speech. The prompt template might look like this. Is this hate speech or not hate speech? When a hate speech sample is put through the template, it might have outputs such as it's hate speech, or even hate speech, because it uses negative language against a racial group. This variance in response formats is difficult to parse consistently. Improved prompting can help, but only to a certain extent. There are 3 design decisions in answer engineering: the choice of the answer space, the answer shape, and the answer extractor. Leo et al. Defined the first 2 as necessary components of answer engineering, and we append the third. We consider answer engineering to be distinct from prompt engineering, but extremely closely related. The processes are often conducted in tandem. So figure 2.13, LMM response. Answer shape, the span of the tokens. Answer space, the all possible spans of the tokens. And the answer extraction, selecting the proper label. So the annotated output for a large language model output for a labeling task shows the 3 design decisions: choice of shape, space, and extractor. Since this is an output from a classification task, the answer shape could be restricted to a single token, and the answer shape space to one of 2 tokens, positive or negative, although they are unrestricted in this image. So the answer shape, the shape of an answer is its physical format. For example, it could be a token, a span of tokens, or an image or a video. It is sometimes useful to restrict the output shape of a large language model to a single token for tasks like binary classification. The answer space is the domain of values that its structure may contain. This may simply be the space of all tokens, or in a binary labeling task could just be 2 possible tokens. Answer extractor, in cases where it is impossible to entirely control the answer space, such as consumer-facing large language models, or the expected answer may be located elsewhere within the model output, a rule can be defined to extract the final answer. This rule is often a simple function, such as a regular expression, but can also use a separate large language model to extract the answer. Okay, now we're into the verbalizer et al. Verbalizer, often used in labeling tasks, a verbalizer maps a token, span, or other type of output to a label and vice versa. For example, if we wish for a model to predict whether a tweet is positive or negative, we could prompt it to output either plus or minus, and a verbalizer would map these token sequences to the appropriate labels. The selection of a verbalizer constitutes a component of answer engineering. And we use a different definition than Liu et al. With respect to granularity, token versus span, since the output could be that of a different modality. See, I think of it as span, but I hear you. All right, regex. As mentioned previously, regular expressions are often used to extract answers. They are usually used to search for the first instance of a label. However, depending on the output format and whether chain of thoughts are generated, it may be better to search for the last instance. Separate large language models, sometimes outputs are so complicated, regex don't work consistently. In this case, it may be useful to have a separate large language model evaluate the output and extract an answer. This separate large language model will often use an answer trigger. The answer yes, no is to extract the answer. And then we will be on to part 3 momentarily, because I am definitely splitting this thing. It's very long. We are only 20 pages out of 80 in, or 20 pages out of the 40 we were going to talk about. So yes, this is probably going to be an hour and a half at minimum.